And I will continue in the with the scaling problem, more or less, as you will see, as we are trying to get time information in metamorphic systems out of diffusion zoning patterns. And if you look at diffusion chronometry, it started out and it was heavily applied to igneous systems at first. And the reason for that is quite simple. Firstly, all the diffusion experiments, the diffusion coefficients are determined at temperatures that are high enough in order to produce diffusion profiles that can be measured by various analytical techniques. And so the application of these diffusion data is in the area where you would where your igneous systems are sitting. Then you have, if you, for example, determine timescales of resident times of crystals in magma chambers, plumbing systems. So I saw Maren is in the audience. Maren Karl et al. Did a lot of work there. Your boundary conditions are quite, or can be simplified in as that you can assume constant composition, for example, or controlled composition at the boundary. And you often deal with isothermal problems, which makes the numerical modeling quite straightforward, and you have relatively short time scales to model. If you go into metamorphic systems, in contrast, you actually have to deal with heating or cooling because you go along the PT path and you may have to take into account the pressure effect. The other problem is that if we are looking at the temperatures we are dealing with at typical metamorphic systems, we are basically here on our diagram here of this Arrhenius plot. This is the area where our Arrhenius relationships can only be extrapolated to and are not really well constrained. And so a little error in here leads to a bigger error down here, which was always one of the largest point of critiques when it came to diffusion chronometry at metamorphic systems. The other thing that we have to take into account are actually the mineral reactions itself. So we have to dissolve stuff, we have to transport stuff by diffusion, and we have to precipitate this. So it's not only a diffusive exchange, but there's a lot of net reactions occurring at the same time. So essentially, we also deal with longer timescales, not only in the question of days or years, but in 10,000s of years to million years of scales. So in a sense, the metamorphic systems are much more sluggish. And in a way, we use this concept of sluggish reaction time in metamorphic systems for our concept of geothermobarometry, right? Because in equilibrium, we assume element partitioning in between coexisting minerals according to their partition coefficient. And we use this for the famous garnet and biotite, OPX, CPX, or any kind of exchange thermometer that you can think of. But essentially, this is only applicable for where you have a net diffusive exchange. As soon as you have an entire reaction going on, you have to dissolve your material, you have to transport it, you have to attach it, and then homogenize. So these processes, these homogenization processes, are also occurring by diffusion, and we can trace them. So knowing the timescales that we use or that we need in order to make these processes happening allow us to actually get timescales straight out of the diffusion profiles or the zoning patterns. But what's the classical approach for us to get time information for metamorphic systems? So one of the things is we can date minerals. And if we know the closure temperature of these minerals, we can actually make a statement at which point in time the mineral has been. So if we look at the closure temperature of white mica, for example, for the rubidium-strontium system, let's assume this is at 500 degrees C. So if we go for a typical metamorphic cycle, we would have increase in pressure and temperature. And if our mica would form at these peak conditions, the system would remain open. So as long as the metamorphic event continues, as long as the PT path is above the closure temperature, we are basically not closing our geological clock. And so we are losing the information of the formation, but we know when the mica is actually passing the time of the closure temperature. So this is what we essentially call a cooling age. If we would have a mica that is formed below that stage, so below the closure temperature, we would call that the crystallization age. So depending on the position of the event, so nucleation and growth, and the closure temperature, we can date different points in time. If we would now apply a different system to the same mica, let's say argon-argon, which has a lower closure temperatures, we would get a second age out of this, the age when the mica is passing the 400-degree line. So if we know these closure temperatures and we know the processes we want to trace, we can actually determine the time span, the time period in between the crystallization and the type of cooling. So this is the classical approach that has been applied over decades. And as you can see here on the upper left, you have a different range of closure temperatures for different systems. And if you apply these to various systems in your rock, or even for different rocks in the same area, you can actually constrain different PT path and pin times on that. So for example, in that case, we would determine the formation using uranium, lead, and zircon. We would get an age of 341 million years, and a cooling age for the argon, and mica for 333 million years. So the entire PT loop would take us roughly 8 million years. Done and dusted. But the point here, the important point here is, in order to do so, you really need to be aware of your closure temperature. So let's have a look for the definition of the closure temperature, which you can see here, where your closure temperature, Tc, is basically a function of a various set of variables. And they include geometry, for example. Do we have a platy mineral? Do we have a spherical mineral? Because this is, of course, affecting our diffusion. We are looking at the diffusion properties, so the diffusion coefficient and the activation energy. And we are looking at the cooling rate. And if we have an idea on the cooling rate, we can iteratively solve that equation to get a guess for the closure temperature. So this is risky in itself because you basically have to put in an unknown in order to get something that you don't know. So you basically have an unknown. The other thing is, if you carefully look at the Dodson equation, it's only justified for a number of assumptions. And one of them is you have an infinite reservoir of material. So you have an infinite reservoir of the element you want to diffuse. And as soon as you are on the boundary of this, of your phase, the element is infinitely fast transported away in order to keep the diffusive flux up. Yeah. So as soon as basically the element is leaving the crystal lattice, it needs to disappear in order to make space for new material. Well, and this is, of course, something that is not really true for metamorphic systems, right? If we look at different Arrhenius plots, diffusion coefficients for ferromagnesium minerals, you can see that they differ quite substantially. So in other words, if I want to have a diffusive exchange in between two minerals, the assumption of an infinite reservoir is not given, right? Because if you're, for example, if you are in an olivine grain, the material that is coming from your CPX grain is homogenized in your olivine grain much faster than the you're going from the olivine grain into the CPX grain, so you have no problem supplying material, but you have problems homogenizing, so you basically are rate limited by your CPX. All right. So the assumption of an infinite reservoir and infinitely fast transport is actually not really true for metamorphic systems. And so the closure temperature, as we know it from Dodson, is strictly not applicable. So we need, in order to solve this problem, we actually need to look at the diffusive fluxes across the boundary. And here we developed a model a couple of years ago where you have a garnet crystal on the left-hand side, a clinopyroxene on the right-hand side. You have initial distribution of concentration shown here in the red dashed line. And what you actually do is you determine the fractionation using the partition coefficient in between these two phases. And you have to calculate the diffusive fluxes across this boundary, which basically means everything that goes in, that goes out here needs to get in here and vice versa. So these diffusive fluxes have to be the same. And this is something that people need to be really aware of, that when you look at diffusion data, often you read in the literature that people are looking at the diffusion coefficients and make an interpretation what is diffusing fast and what is diffusing slow, which is simply not true. You have to look at the diffusive fluxes. So you need to have a look at the gradients in the chemical potential, and this will determine how much material is actually flowing or diffusing through your crystal. So the diffusive flux is something fundamentally different from your diffusion coefficient. So if you start modeling this numerically, you can actually start looking at the development of these zoning profiles. And you immediately see the effect of the different diffusivities. Here we are on the left-hand side, we are cooling down from 1300 degrees with a specified cooling rate, so 10 degrees per million year, 100 degrees, and 1000 degrees per million year. Here we have peak temperatures of 900 degrees and the same three cooling rates. And as time progresses, as you can see, from 10 to 15 million years, you see the development of the zoning profiles in both minerals, and you can see that the clinopyroxene zoning pattern is much more pronounced than the one that develops in the garnet. And the reason for this is simply that the diffusion in clinopyroxene is slower. So the clinopyroxene has, speaking in pictures, problems to get more material onto the surface, onto the interface, in order to supply supply the garnet. The other thing that you can see is that in almost all cases, at least if you go from high temperatures, even the composition in the core of the garnet has been changed. So both cores, core compositions have been changed, not only the rims. So the classical approach that you do core concentrations to get the temperature for the onset of garnet growth, for example, and rim for the end, that is just not true. That's not applicable. Yeah, you can easily change the interior of your grain and still have a zoning pattern in there. We can also translate this into the recorded temperatures, which would basically mean basically the effective closure temperatures. So in here you see the temperature that would be the real temperature against the one that is recorded in your zoning profile if you would take the composition and determine the temperature from that. And even though the diagram looks a little bit complex, it's basically just you get the composition that you would have for a core temperature or rim temperature in dashed or solid lines respectively. And we do this for 3 different grain sizes, and you can see how the closure temperatures basically vary as a function of the grain diameter. We know that from the Dodson equation, and the cooling rate. We know that from the Dodson equation as well. But they also vary about as a function of their diffusive flux, and so we can get a whole set of different closure temperatures. So it's not that you're looking in your system that micas have enclosure temperatures of 500 degrees, you can exactly determine where your grain is closing if you calculate the diffusive fluxes properly. So just to give you an example where we can apply those, because all of these models that I showed you have been for numerical models in between two crystals on the nanometer to micrometer scale. The diffusion experiments are typically done on the hours of and the order of hours to days, and of course we know perfectly well our system. In the field, that looks quite differently, right? So we have a lot of composite rocks where we have multiple phases in there. There are large-scale geodynamic processes that affects the PT distribution, and the timescales are much longer. So it's harder to actually get it well constrained. And the example I would like to show you is from the Granolite massif in Germany, where you basically have here the famous type locality of your Granolite block, which is surrounded by a corona of a schist, a rim of a schist, and another area surrounding there where you have phyllites, right? So low temperatures. If you look at the cross section that has been published, you see the granolite complex in here with the different covers with the mantle schist and the phyllite cover. And in this granolite block, you have garnet peridotites, which are sitting somewhere here inside the granolite block. They are sitting here. And in these garnet peridotites, you do see former megacrysts of alternating garnet and clinopyroxene lamellae, right? So it's clearly an exsolution feature where either a garnet has been exsolved from a clinopyroxene or a clinopyroxene from a majority garnet. And as a matter of fact, the PT path that I did show you earlier on are actually from this type locality where a number of authors have tried to put different information together in order to constrain the PT path and constrain time information to that. And we have been now interested in looking at these lamellae, where you have a really nice and well-defined geometry, and where you can, because of the scale here, you can easily apply a simple 1D model to the interior part here and model the element exchange in between these two lamellae. And we have been interested to see what kind of information can we actually get out of these diffusion profiles, out of these zoning profiles, in order to see whether this matches the PT evolution or produces something different. So looking at the major elements, this is quite boring. So the clinopyroxene doesn't show a lot, basically nothing significant. We do see some zoning patterns in the pyrope component, in the grossular component, as well as the almandine component. More importantly, we do not see any zoning patterns for the chromium or any trace elements in the garnet, but we do see these remarkable profiles or this remarkable zoning in chromium and titanium in the clinopyroxene. So we use this as an interpretation to conclude that most likely the garnet has been exsolved out of the clinopyroxene and not vice versa, as the chromium and the titanium are piling up in the clinopyroxene, which is in front of the growing lamellae, which would be back diffusion, as has been observed in other minerals by CC, for example, CC Cruz-Uribe back in 2014. So we solved already one of our questions. So the garnet is exsolving from the clinopyroxene, which makes our life much easier, because otherwise we would have a quite strange garnet composition. Now let's have a look at our models, the application of these models, and we use different cases here. So the first one, starting easy, we have an isobaric cooling from about 1,000 degrees, because we know everything above 1,000 degrees we can't resolve in our diffusion profile anyway, and 600 degrees where we expect our profile to freeze in more or less. So we choose basically the final, we choose the depth where we expect our granulite block to have been emplaced, and we did model different times with a starting composition once again here in red, and then the time evolving from black to blue to green. And you can see that we can match the garnet profile quite nicely. Well, the clinopyroxene profile doesn't do a lot. But what is remarkable is if you add exhumation to the story, right? So as soon as you add exhumation, as we did here, so we have the same temperature time path, but we add changes in pressure. So if we add changes in pressure and we start at greater depth and go to our final intrusion or emplacement depth in the same time frame, then we observe that the partition coefficient is actually working against us. Yeah, so in other words, if we would have exhumation contemporaneous to the cooling, then we should definitely see something in our clinopyroxene, because the partitioning should be much stronger. So this is an indication that this stuff has been quite hot, quite shallow, and cooled quite rapidly. And then we said, okay, well, let's be fancy, because these exsolution lamellae are actually growing. So we added a growth component to our model and said, okay, we start with a small lamellae of half of its current size, and then move the boundary to its current place. And let's see how we can change how this is affecting the profile. We have shown this for fast-growing crystals back in 2009, that we can really have an effect on the recorded diffusion profiles. In this case, it doesn't do a lot to the story. It changes the story a little bit. It matches the garnet profile a little bit better. And once again, for the clinopyroxene, this is all within the uncertainty. But taking this together, this all strongly points to the fact that the zoning pattern, if they are clearly if they are stemming from diffusion, they would indicate fast cooling at isobaric conditions. So putting that together, this would basically mean that in our world, we would have a much steeper PT path, so that we have hot, shallow temperatures here, and then rapid cooling going over here. And while we have no clue how long that process will take, we can determine that this part of the process will take place in less than 10,000 years. And all of a sudden, this rings a bell, right? Where do we have isobaric fast cooling in less than 10,000 years? This sounds quite awfully like a contact aureole. So we can check for this, right? Because we cannot only model the diffusion of elements, we can also model the diffusion of heat. And so if we go back to our geological map, and we take a cross section here through the contact aureole, where we have the granulite block here, all the way through the mantle schist and the phyllite. So the granulite block would be this part, the schist mantle here, the phyllite over there. The dashed line marks the position of the garnet peridotite. And we have an estimate for the emplacement temperature of 900 degrees as we modeled those in the diffusion profiles. We can actually extract a temperature time profile for a rock that would be at the position of the garnet peridotite, which would be this one over here in the upper left. And you can nicely see that you have a quite quick drop down to the 600 degrees in less than 10,000 years, as we would expect as we have modeled this for the element diffusion. So this really nicely fits, and it's a completely independent constraint, and both of them are actually telling us the same story, that we have some sort of isobaric cooling taking place. So the question is now how to get this stuff up at without losing a lot of temperature. There are geodynamic models for that. And this is basically the input that you can give as a petrologist, as a diffusion modeler, towards the tectonic models, right? Because whatever tectonic model you are applying now, it has to fulfill these boundary conditions that you have to bring this stuff up with a temperature of 900 degrees in order to produce your nice contact metamorphism over here. So to wrap it up, it's basically, even though that we are at quite low temperatures, we can use these chemical zoning profiles in order to constrain time information. And the beauty about the system is that we can do this on a single thin section. We do not need different isotopic systems or different mineral assemblages in order to get the entire PT path, basically like a jigsaw puzzle. You can get the full information out of a single profile. And if you have multiple diffusion profiles within a single rock, multiple mineral phases, for example, then you can cross-check yourself. The critical part is that we need to know how diffusion, the diffusive parameters. So we need to know who is basically, which mineral is talking to which, in order to constrain the diffusive fluxes, because only if we can constrain the diffusive fluxes, we can get reasonable timescales out of this. So for the friends of the Variscan, the Granolite complex was in place quite quickly and at high temperatures, and produced a very nice contact aureole. And so these are basically the potentials of diffusion modeling in metamorphic systems. And I hope you enjoyed the talk, and I'm happy to answer any questions you may have. So I think I need to moderate my own questions in this case. So Bob is asking, what's the potential for this approach where you do not have the very simple geometry you describe? Yeah, that's a big problem, right? We do need the geometrical constraints, and this is even true. I mean, what I've shown you is a simple 1D model, because these lamellae have an aspect ratio which basically allows us to neglect any diffusion in a second dimension here. There is a dangerous tendency that I observe for diffusion models, that a lot of people think if you go to higher dimensions, 2-dimensional models, 3-dimensional models, they are getting more accurate. That's not the case. So what you need to do is really think about your geometry before you start modeling. This is the very crucial part. If you do not have real constraints on the geometry, you are immediately introducing a large error. Any more questions? Can you apply these ideas to any X-solution lamella, do you think? In principle, I would think so. Yeah, what we need is basically the right kinetic window, the right combination of diffusivity and growth and fast growth in order to produce the profiles. As long as we have knowledge of the diffusive parameters and the profiles, we should be able to do this. And I think there's a higher potential, and as better the analytical work gets, as more we can get small scale profiles, as better we will get there. The problem is at 500, 600 degrees in our world of metamorphism, these things don't travel fast and far.
No, but I guess when you've got a symplectite as well, they tend to coarsen up over time as well. Yep. So I guess that would also cause complications, wouldn't it?
Yes, and as soon as you introduce net reactions, right, where you have dissolution and growth, I mean, our model, which has the growth component in there, that took me a lot of headache to introduce this, because to balance the diffusive fluxes across a moving boundary, is basically at the top end of my numerical skill set. Let's put it that way.
We explained it very clearly. So thank you.
What would happen if you introduce fluid into the system? Well, no fluids, no party, right? So as soon as you have fluids in the system, you will enter the world of dissolution precipitation, all right? And so one of the things that are going to happen is that all the element transport along the grain boundaries will become faster, and we are back in Tinker's domain here. So it changes the boundary conditions in a way that you're closer to the original assumptions from Dodson. That's what I would say. But in most systems, I would assume that you're running into trouble as soon as you start to dissolve and precipitate stuff. Do you have to worry about lamellae interacting with the rest of the rock? Yes, right? And the beauty about the system that I've shown, and yeah, there's a reason why I've shown this, is because I can pick a lamellae that is in a megacrystal that is very unlikely to talk to the rest of the thin section. In that case, I don't have to worry about that. But as soon as you have any interaction with the of the lamellae that in may it be through cracks or along the interfaces of the lamellae, you will have fluxes from the outside. And the same is true if you think of garnet biotite thermometry, for example. How easy, if we be honest, how well do we know which garnet is talking to which biotite in this rock, right? And so you will have fluxes from all directions, and constraining those fluxes comes back to, can I get sufficient control over the geometry in order to get a meaningful model system up? I hope that answers your question.
The one?
Yeah.
What about the possibility that some of the inhomogeneity in your lamellae are related to growth of the lamellae? For example, when you initiate a lamella, aren't there likely to be lattice strain effects on the composition?
Yes, and in a simple case, I've shown that at the same time, right? I showed you the trace element profiles, where I would argue that the growing lamellae is actually piling up the rather incompatible elements of chromium and titanium and garnet in the clinopyroxene, which is then trying to rehomogenize the clinopyroxene part. Right. In this case, you're looking at a growth profile rather than a diffusion profile, right? Which will eventually become a diffusion profile. But of course, you can introduce growth profiles as well. If you're looking at our 2009 paper where we modeled these fast-growing crystals that are piling up and keeping even at an isothermal condition, you produce a growth zoning inside the fast-growing mineral. And you can translate this into isotope ratios or simple element zoning. But it's always a question of how fast are you growing relative to how fast are you diffusing. This is the critical ratio which you have to look for.